In the 11th lecture of Symmetries, Particles and Fields, we're going to look at this Lorentz algebra, the Lie algebra of the Lorentz group that we've just derived in lecture 10. And we're going to see how spinor representations come out of that. In fact, we'll see the emergence of the Dirac spinner, as it actually comes out to be a direct sum of other spinors. And then we'll go on to look at the Poincare group. So we'll add translations symmetry into the mix. And we'll derive the Lie algebra of the Poincare group. And we'll finish with a brief summary of the upshot of what happens with representations on quantum states of the Poincare group and the Poincare Lie algebra. We won't cover them in detail now. We'll find it convenient to leave that until the end of the course, because there's a few things that would be nice to explain to you in terms of group theory in more general terms in between. Okay, so this that we derived at the end of last lecture is the Lorentz Lie algebra. Okay, so to get from the previous line to this takes about three or four lines of algebra. You can see those lines in the book if you are having difficulty doing them for yourself. So what I want to do is look at this Lorentz Lie algebra in more detail now and separate out some the space part of it first. So first of all, I'm going to lower all the indices, which we can do with etas. Okay, and then I'm going to put I, J, K, and L in for the indices, indicating that they take values between 1 and 3. So I'm just going to write down the Lie algebra again with the Roman indices, which range from 1 to 3. And now the metric becomes minus delta in the space indices. So we get a minus delta JK MIL. So notice there's going to be 4 terms, and in some of the terms I will have taken the relation that we have where Mij is equal to minus Mji. So we have to remember, you have to remember in deriving this that we have anti-symmetry of the indices of the m's. So minus delta Ik Mjl minus delta Jl Mik plus delta Il Mjk. All right, now I want to define another operator, which is a function of the Mij's, and you'll see why I've called it Jm in a moment. But we define this to be half epsilon Mij times Mij, which implies that, so if you multiply both sides of this by an epsilon symbol, you can derive that Mij is equal to epsilon Ijm Jm. Okay, so we've got the relationship both ways between the J's and the M's. So now the Lorentz Lie algebra. So this Lie bracket, then we can write this in terms of the J's. So we have to multiply it by some epsilon symbols, but there's a few lines just to work out that this implies that the Lie bracket between Jm and Jn is epsilon mnl jl. Now, this algebra we've seen before. This is the Lie algebra of So3, or indeed of Su2. So where you have three of these J's. And of course, this is equivalent to the Lie algebra of the angular commutation relations. So the angular momentum. So we shouldn't actually be surprised at this, because we already said that purely spatial Lorentz transformations that are connected to the identity are rotations. At least the ones connected to the identity. Okay, so now I want to take our Lorentz algebra and I'm going to allow myself one of these indices, so it'll be rho, to be 0, and the other ones I'm going to set to be spatial ones. So we have one time index and the rest are spatial. Oh, let me write this on the new line. So two of the terms go away because we get Minkowski metric and the 0th component, which is of course 0. And if I allow myself two of the indices to be time-like, then we get the other bracket. Which is this one. Okay, so if I'm going to introduce some new notation, actually two sets of new notation, unfortunately. But to start with, I want to introduce something that generates boosts. And it's going to be this 0th component of M. So we write Ki is M0I. So just physically, this generates a boost, a Lorentz boost in the ith direction. And these are anti-Hermitian generators. Okay, so then our two previous commutation relations written in this new notation. So we've got the J's as well. these become the following. So we've got Ji, big K, J is epsilon ijk, K suffix K, and there's a commutation relation between the two Ks as well. Here we get a minus sign, minus I epsilon, epsilon ijk, J suffix K. So you will notice that as previously advertised, the Lie algebra between two different boosts doesn't close, and that's because it's giving us you know, a generator of a rotation, an angular momentum operator. So, okay, if we do another transformation, the Lie algebra becomes clearer, and it makes a point that I want to make here. So the Lie algebra becomes clearer if we take a different basis. So here I want to define some vectors J, and they're either going to be J plus or J minus. So these are defined to be a half times J plus IK vectorially, plus or minus IK, I should say. Okay. So you can check that this implies that J plus Hermitian conjugate is equal to minus J minus, for instance. So this is neither a Hermitian nor an anti-Hermitian basis. Nevertheless, we take this new basis and we rewrite our commutation relations now. And they become the following: J plus minus I, J plus minus J. So this is the commutation relation when, or the Lie bracket, when we have the same sign on the J's. You can calculate this and we get epsilon ijk jk plus or minus. And then if we take the commutator of ji plus with j minus, for any I or j, we get 0. So j plus looks like the Lie algebra of SU2. It satisfies the Lie algebra of SU2. The j minuses look like they satisfy the Lie algebra of SU2, and there is no non-trivial commutator between the pluses and the minuses. So what that means is that the Lie algebra of SO1, 3 is isomorphic to the Lie algebra of SU2 in a direct sum. Another Lie algebra of SU2. So in other words, there are two commuting copies of angular momentum operators. Now, what I'm going to call this first one, I'm going to call the left SU2, or the left Lie algebra of SU2. Actually, let's say this. This is the left SU2, and this is the right SU2. Okay, so of course these act, these two SU2s, or the Lie algebras, act on a representation space, and it's a direct sum. And so when you exponentiate the SU2s, the left SU2 and the right SU2 will also act on the same representation space. And those two representation spaces that we direct sum, each one of them is just a two-component object, and that's a spinor of the Lorentz group. So we get two spinors of the Lorentz group, and they're doublets of of the left SU2 or of the right hand one, of the right one. And indeed, you'll hear people referring to them as left-handed and right-handed spinors. Okay, so let's discuss spinors a little now. So we have spinors of SO1, 3, just like we did in SO3, actually. So we define a strange thing. It's a kind of generalization of the Pauli matrices to SO1, 3. So we define a sigma mu. So this is going to be a 4-vector, but each element of the 4-vector is a 2x2 matrix. So this is I2 in the 0th component, and it's got the Pauli matrices in the next 3 components. And a sigma bar mu is defined as I and minus sigma. So notice that these are Hermitian. The Pauli matrices are Hermitian. So for a 2x2 matrix, which I'm going to call A, this is in SL2C. So they're unit determinant, but otherwise they're 2x2 complex matrices. Then we have a map in between our members of the Lorentz group and these matrices. So it's an exercise that's brought out for you in the book. It takes you through how to prove these two relations, or to obtain these two relations. So we can write the map from the matrices A to a Lorentz transformation in the following way. Take half times the trace of sigma bar mu A sigma nu sigma A Hermitian conjugate, and in the other direction, A is plus or minus sigma mu lambda mu nu sigma bar nu divided by square root of 2 lambda mu mu. So this takes us on a map between SO1, 3 and SL2C. But of course, we have this Z2 given by the two different signs of A. So we have that SO1, 3 is isomorphic through this map of SL2C over Z2. Now, of course, the covering group of this SL2C over Z2, the universal cover, is just SL2C. So we write that in the following way. So of course, SL2C coset Z2 is disconnected, but if we take the universal cover, we've just got SL2C. So now let's look at our representation space spinors of Lie algebra of SU2, the left-handed one, plus the Lie algebra of the right-handed one. So now I have some spinor, say psi alpha. So alpha goes from 1 to 2, and under SL2C, this goes to A alpha beta psi beta. Where alpha and beta are in 1 and 2. Okay, so that's our spinor of, say, the left-handed SU2. And we have psi beta goes to psi beta a to the minus 1 beta alpha. Now, the inverse of 2 by 2 matrix has some special properties, and you can write it just in terms of the original one and the determinant, which of course is 1, and some epsilon symbols. So it turns out that if we define psi beta is epsilon beta alpha psi alpha, this works. Okay. So that's for the left-handed SU2. For the right-handed, so we have indices alpha and beta, etc. For the left-handed one, we're going to have indices alpha dot and beta dot for the right-handed SU2, and so psi bar alpha dot under A. Well, this goes to psi beta dot A bar to the minus 1 beta dot alpha dot, where this A bar to the minus 1 beta dot alpha dot is A alpha beta complex conjugate. Okay, so it's the Hermitian conjugate actually, because I've reversed the order of the row and column indices. And we have chi bar of alpha dot going to A bar alpha dot beta dot chi bar beta dot. So we have two independent fundamental spinors. And I can take these to be, say, psi alpha and psi chi bar alpha dot, and these can be combined in a direct sum to make the Dirac spinner, which is the one that's most familiar probably to us. So we write this as big psi, and this is defined to be, so it's a 4 vector. Well, it's a column with 4 entries, and the top 2 are psi alpha, and the bottom 2 correspond to chi bar alpha dot. And note here that both A and A bar are in SL2, C. Okay, so how do we consider sort of representations made out of tensors, and how do they transform under the Lorentz group? Well, we have invariant tensors, the following invariant tensors. Remember, it's always important to identify the invariant tensors. Epsilon, mu, nu, rho, sigma. And so whichever, so you define one of these to be +1. So let's say that epsilon 0, 1, 2, 3 is +1. Okay. Then this implies, by raising all the indices with some eta, some Minkowski metrics, this implies that epsilon with the indices upstairs is -1. So you have to be careful. And tensors which have this property, where there's a sign change and they're going from bottom indices to top indices, are called pseudo tensors, rather than a tensor. There's a pseudo tensor. So that's one invariant tensor. And we also have eta mu nu, of course the inverse, and epsilon alpha beta, epsilon alpha beta, epsilon alpha dot beta dot, and epsilon alpha dot beta dot. So we have a lot of invariant tensors to play with. So we have these kind of 2 different styles of indices, if you like, 2 different classes of indices. One of them is vector indices, mu, nu, rho, sigma, that go from 0 to 3. And the other ones are these spinorial indices, either left or right-handed. And so we get different kinds of tensors. So a general vectorial tensor, these transform as, so let's take T, and let's call these indices mu1 to mu n, and nu1 to nu n, m. So under a Lorentz transformation, for all of the upstairs, the contravariant indices, remember, we define that to give us a lambda. So just an element of the Lorentz group. And for all of the downstairs, the covariant indices, these give us a lambda to the -1. Times t alpha 1 to alpha n, beta 1 to beta n, where all of these indices are in the set 0, 1, 2, 3. So for a general spinorial representation, we lower all the indices using epsilons first. Then I can write this tensor upsilon. And let's say it's got, so 2j downstairs indices, sorry, 2j undotted indices and 2j bar dotted indices. So here now the indices are in 1 and 2. So these are spinorial indices. So this goes to, well, for each undotted index, we get a factor of A, which is in SL2C. And then for the dotted indices, we get A to the minus 1s. Oh, sorry, A bar to the minus 1s, A bar to the minus 1, beta 2j dot alpha 2j dot. Okay, to make sure you get an irreducible representation space out of this, then we must ensure that this upsilon is symmetric in each set of indices. So it has to be symmetric under the left SU2 indices and symmetric under the right-hand ones. So the spin of this under the left SU2 is 2j plus 1. The dimension, sorry, is 2j plus 1. The dimension under the right-handed SU2 is 2j bar plus 1. So the dimension of the whole tensor representation is 2j plus 1 times 2j bar plus 1. So we have a notation where spinor representation we can write as j and j bar. So this is, you know, the total spin under left SU2, and this is the total spin under the right SU2. So as I said, Dirac spinners are then are in the half 0 plus 0 1/2 representation. it's just the direct sum of a left-handed fundamental spinor and a right-handed one. So the important thing to notice is that conjugation, this switches the SU2 lefts and the SU2 rights. So this sends J and J bar to J bar and J. So yeah, okay. But you can translate this into field theory. You'll learn more about this in the quantum field theory course if you're doing it, if you're studying it. But you can take the conjugate of a left-handed spinor and obtain a right-handed one, is what this means. All right, so let's switch now to the Poincare group. This is called, often called ISO 1,3. And what this means, this translates as the isometries of four-dimensional Minkowski space. So that's why it's called ISO. And so we take the symmetries of the Lorentz group and we add translations to those. So, of course, the idea here is that laws of physics shouldn't change on whether you do your experiment here or in India, or indeed whether you do it today or tomorrow, or any mixture of those two things. So the symmetry is saying that the physics should be the same when you transform your space-time coordinates to a new one, which is now Lorentz transformed old ones plus some shift a mu. So what we call the element of the Poincare group we denote this as lambda comma a here. All right. So, right. Now, so what happens if we do two successive Poincare transformations? We better check that the group closes, that we get something that's akin to a different element of the Poincare group. So let's act on lambda 1a1 with lambda 2a2. Well, here we get lambda 2, lambda 1, and lambda 2 a1 plus a2. So you can derive this just from the above transformation on x mu. So this form is also an element of the Poincare group. So the group closes under the group composition. And if you look and see, this is actually a semi-direct product, and it's the semi-direct product of the Lorentz group with the translations. So T4 is the group of translations in 4 dimensions. Well, it's an abelian group, but that's the deal. So this group, SO 1,3, ISO 1,3 is 10-dimensional. And it acts, of course, on these x mu's, so it just acts on the Minkowski space M4. So we call this Minkowski space curly M4. So at any one point in this Minkowski space, the isotropy group is the Lorentz group. So curly M4 is a coset of the Poincare group with the Lorentz group. All right. So in other words, we allow ourselves Poincare transformations, but we identify any points in this total space which are related by Lorentz transformations. Remember, the Lorentz group is 6-dimensional. So what's the identity element of the Poincare transformation, Poincare group? Well, it's when we don't do a Lorentz boost and we don't do a translation. So it's written like that. And you can check that this, with the group composition law, implies that the inverse element is just the inverse Lorentz boost, and we take minus lambda 1, lambda to the minus 1a. Okay, so you can always write an element of the Poincare group. So we can write a general element as, well, that's lambda comma a. We can write it as, first of all, you do a Lorentz transformation and then you do the translation. Write it in this form. But the ordering here is, of course, important. All right, so much as we did in the Lorentz group case, we want to calculate the Lie algebra of the Poincare group. I think we've got time to do that. And we take a commutator of 2 elements, just as we did in the Lorentz group case. So we're going to call this lambda c comma ac. So this is that c stands for commutator, and we're going to take the commutator of 2 elements. So it'd be lambda 2 a2 to the minus 1, lambda 1 a1 to the minus 1, lambda 2 comma a2, lambda 1 comma a1. So it's an exercise here to use the rules above and just check and you should be able to get that lambda c is just almost trivially the following, and ac is lambda 2 to the minus 1, lambda 1 to the minus 1, lambda 2 a1 minus lambda 1 a2 minus a1 plus a2. There's a few lines, 4 lines or so, to derive that, and it's laid out for you in the book if you're having trouble. Now, okay, so exactly, well, analogously as with the Lorentz group discussion, we now consider small changes. So in other words, lambda I, I'm going to be put to be equal to the identity matrix plus omega I, just as we did before. Now, so strictly speaking, you know, you can put mu nu matrix indices on these. Okay, and if you do that, you will find, and you substitute the lambdas into this equation for AC, you should find that AC mu is equal to lambda 2 A1 minus, omega 2 A1 minus omega 1 A2 mu plus some other terms, and we're not interested in the other terms basically. So these are terms of order omega I AI, where the indices are the same, and order AI squared and order omega I squared. Okay, so the only terms we're really interested in are omega I AJ, where I and J are different. Okay, so in a quantum field theory, we have some associated unitary operators. So U of lambda 2 A2, U of lambda 1 A1. So the group composition on quantum states tells you you should get this. And so now what we do is we expand U of lambda A. So now I'm going to put lambda of some small parameters, some small parameter omega in. And this operator, this unitary operator, becomes 1 plus a half omega mu nu m mu nu plus a mu big P mu. So this big P mu, this is a translation operator. It acts on quantum states. That's a translation operator. M, these big M's, as we said before, these are now promoted to operators that act on quantum states, give back eigenvalues of, well, angular momentum, etc. Okay, so this operator also has these terms of order omega squared, A squared, and A omega. Okay, so from the group composition rules, this unitary operator, the inverse unitary operator, is the unitary operator of lambda to the -1 and minus lambda to the -1a, which is 1 minus a half omega mu nu m mu nu minus a mu p mu. Again, plus omega order omega squared, order a squared, and order a omega. Okay. I think we have actually run out of time now. So we will finish this off at the start of the next lecture, where we're almost there. We've just got a bit more algebra to do, and the Poincare Lie algebra will pop out. And in fact, as part of that, the Lorentz algebra will pop out as well. Thank you.